Good morning, students. In this class, we will learn graphical method for solving linear programming problems involving two variables. This method is applicable to linear programming problems having only two variables. It cannot be applied to problems having more than two variables. First, consider all constraints as equations and then plot them on graph. After this, consider the actual signs of constraints. For greater than equal to type constraint, the area on or above the constraint line, that is away from the origin, and for less than equal to type of constraint, the area on or below the constraint line, that is towards origin, will be considered. The area common to all the constraints is called feasible region and is shown as shaded in the graph. Any point on or within the shaded region represents a feasible solution to the given problem. Now next, find the coordinates of each corner point or extreme point of the feasible region. Find the value of the objective function at each extreme point. The point at which the objective function is maximum or minimum is called the optimal point, and its coordinates give us the optimal solution. So let us now take an example. Okay, this is a example where all the constraints are less than equal to type and the objective function is of maximization type. Okay, so we will solve it considering the constraints as equations. So x1 plus x2 equal to 450 to x1 plus x2 is equal to 600. Now plotting these two on the graph. Okay, so now these two equalities represents two straight lines. Okay, so now how do we do it? How do we this present these lines on the graph? So from the first, okay, I tell you the way what to do. Put x2 equal to 0, we get the value of x1, so that value will be on x-axis. Similarly, put x1 equal to 0, we get some value on y-axis, x2 axis. Okay, and similarly from here, if I put x2 equal to 0, I get x1 equal to 300, so point on x-axis, x1 axis, and similarly if I put x1 equal to 0, x2 value will be 600. So these values are, these points are just this joined, the points, the corresponding points of these lines are joined by straight lines, and we get the corresponding straight lines. After that, we consider the actual signs of each constraint. In this problem, both the constraints are of less than equal to type, so area towards origin is considered. So we can see here, so area towards origin here, this line. Similarly, for the second constraint, yes, the lines are towards origin, this side. Now this dark line here and here and this one and this one. So this quadrilateral polygon, this polygon has the common area bounded by this line as well as this line. Okay, so this is my feasible region. Okay, so every point in this feasible region is this feasible solution to the given problem. Sorry. After that, what we do, we find out the coordinates of all these corner points. So here origin 0 0, 300 0, very clear, 0 450 clear. Now we have to find out the coordinates of this point. So this point is the intersection of this line as well as this line. So we solve this. Okay, the coordinates, we solve this like this. To find the coordinates of point B, we solve these two equations. Okay, these two lines. This x1 x2 450 to x1 plus x2 600. So by usual method we solve it, we get x1 equal to this 150 and then x2 is equal to 300. Okay, then we put here. Okay, after that we check the value of objective function at all these corner points. So z at 0 0, z at a 900, z at b 1650, Z at C 1800. So 1800 is maximum. Okay. So the point this 0450 is giving us the highest value to the objective function, and hence x1 equal to 0, x2 equal to 450 is the optimal solution, and the corresponding maximum value is 1800. Okay, this is how we solve this kind of problem. Now we take up a problem involving minimization kind of objective function and all the constraints of greater than equal to type. This is the problem. Same way we consider these inequations as equations first, then we plot them on the graph. After that we consider the actual signs of the constraints and try to find out the common area that we call feasible reason. Okay, so these are the equations. Now we plot them like this. This is the line, this is another line, this is another line, and this is the area away from the origin will be considered. So this is the shaded area is the common area made by these three constraints. Now what are the, we are interested in minimum values, so this is the point, one point, this is another point, and this is the another point. So we have 3 points, 3 corner points of this feasible region where we want to test our objective function. Which of these points is giving us the minimum possible value? So these are the coordinates of this point, and we will find out the coordinates of this point by the same method, and the coordinate of this point is 0 and 40. So for this point B, we have to consider the intersection of line 2 and this is line 1, this is line 3, and this is line 3 and line 2. Okay, so I may have done it somewhere. So first of all, this is how we plot these lines. This is shown, and yes, I have done it here. So 2 and 3 intersection of these two lines here. So solving these, we get x1 equal to 12 and x2 is equal to 4. So now these are my coordinates of these corner points. At this point 0 value, sorry, we will not consider this point, okay, because this is not a corner point. This is by mistake, please ignore this z0 0 is equal to 0. Okay, now this is my first, second, and third. These are my corner points. So at these I get 13,200, 8,800 and 16,000. Okay, so out of all these, which one is minimum? I think this one is minimum. Okay, so since the value of objective function at point B is minimum, so this is optimal solution is given by x1 equal to 12, x2 equal to 4, and minimum value is 8,800. Okay, but there could be other kind of linear programming problems involving reverse kind of inequalities or mixed kind of inequalities. So we will try to see the common area if possible, and then we proceed as usual to determine the corner points of the feasible region, and we solve the LPP.